All right, well, good morning. Welcome to another fun-filled day of calculus. Just to give you an idea of what we're going to be doing today, I do want to talk about the quiz. Not everybody's is graded yet, so if yours hasn't come through, it will be there shortly at some point today. But I do want to go ahead and go over it. So we'll go over the quiz. We'll also go over any kind of homework questions, things like that. And then just so you guys know, I'm going to do things slightly out of order. I'm going to skip section 3.4 and dive into 3.5. We'll come back to 3.4 after. But for today's plan, we're going to do 3.5, which is about the trig functions. And so we'll look at derivatives of the trig functions. We've already done some of that, so it'll be real easy for us to wrap that up. Because I'm doing that switch. I want to let you know that the homework sets, I did change the due dates on 3.4 and 3.5. 3.4 is now going to be due not this coming Monday, but the following Monday. Right, so instead of the 12th, it'll be due the 19th. And then 3.5, I'm moving that up a week so that it will actually be due this Monday, October 12th. All right, so you'll see those in Canvas. You'll see those date changes, but I wanted to mention that here as well. So we're just going to bang out the trig function so we get the derivatives of those, and then we'll spend the rest of the time talking about this exam thing that's coming up on Friday. Kind of help get you to a place where you feel a little bit more comfortable, know what to expect, and so on. So that's the plan for today. But as always, let's go ahead and start with homework questions. I know, Susanna, you said you had something you wanted to look at.
Yeah, I had question 11 and question 14 of 3.3. So 11 was f of x equals 7x to the 6th and then h of x. And then you're supposed to, I think, find the inverse. I believe the question was to find the inverse. I'm not sure. I might have just done a calculation error because they had given us h inverse of x.
We'll go back and we'll look at that. I'll pull that up and look at those. So I'm just making my list here. So 3.3, numbers 11 and 14. Any other ones from other folks?
On 3.2, I had one. I don't know what number it was. It was just a simple derivative. I just got confused on it.
Okay, maybe while when I'm pulling up the homework and stuff, maybe that will buy you time to figure out which one you wanted to see, Leah.
Yeah, I have it written down. I just didn't know what number it was.
Okay. Well, we can do that too. All right. Any others? Okay, well, that sounds good. So, Leah, why don't you go ahead and read me then the one that you have from 3.2. I'll write it down, and then we'll tag it on the whiteboard.
It's just f of x equals 4 times the square root of x minus 6. And I was just trying to figure that out with our rules. I just got confused.
Okay, so when you say you figured out with the rules, you mean the fast rules, not the use the limit definition, or?
Yeah, with the rules that we went over last class.
Okay, all right. We can tackle that one first. Let me go ahead and share my whiteboard here. All right, so let me just make sure that this is what you want, because this is what I heard you say. We've got f of x equals 4 square root of x. Hold on 1 second. How about 4 square root of x minus 6? All right, so does that sound right?
The minus 6 is also under the square root.
Oh, it is. Are you sure?
That's how I wrote it down anyway. Maybe.
Okay. Well, because here's the thing: we don't know how to do this.
Okay.
We haven't talked about the rule that's necessary to do this one. Now, that doesn't necessarily mean that whoever designed the homework for this set, which, by the way, is not me, right? I'm getting this from some other group, but they may have assumed that you or they may have just made a mistake, because this one we have to use what's called the chain rule, and we don't have the chain rule yet.
Okay, yeah, it
Um,
may have actually said to do it the other way, and then I was just trying to see if I could figure it out with our new rules. But okay, yeah.
The other thing, though, is that I'm not really sure, because I don't read the book. I don't know if they've talked about what's called the general power rule. I'm just scanning through the book here real quick to see. No, they don't. So, well, here's what we're going to do. First, I'm going to do it the way that I know we know how to do. And then we'll talk about how we would actually deal with it as the square root of x minus 6 altogether in that square root. Okay. So the trick for this one is, again, to recognize that the square root can be written as an exponent. So does anybody remember what the exponent would be for a square root of x?
1/2.
Yeah, there you go. So this would be the same as x to the 1/2 minus 6. And now when we go and we take our derivative, we can use the power rule on this piece. So the derivative of this thing, let's start, just go term by term. So if we look at this first term, I've got 4 times x to the 1/2. So that 4 is a constant multiple. So it's going to come along. So we have that rule about constant multiples. They just move along down with our derivative. So then we've got x to the 1/2. So how's the power rule work? What do we get as a derivative of that?
1/2 minus 1.
Okay, so the exponent's going to be 1/2 minus 1. So we decrease 1 from the exponent. And there's one other thing we have to do.
1/2 in front.
There you go. We bring that power out front. So the power comes out front as a multiple. So we get 1/2 x to the 1/2 minus 1. All right, so we'll simplify that in a second. But now let's look at the 6. Okay, so we're going to get a minus, because since we're subtracting the two functions, we subtract the two derivatives. But what's the derivative of 6?
0.
Yeah, that one's 0. So constants, when they're by themselves, the derivative is 0. So constants you got to be careful with, because sometimes those constants come along and sometimes they go away, but it all depends what we're doing with that constant. If that constant is being multiplied, it sticks around. If it's being added or subtracted, it goes away. All right, so now let's just simplify this a little bit. So we get f prime of x equals 2, that's your 4 times 1/2, x to the minus 1/2. And I'm going to go ahead and change this back to a square root. It's also going to go into the denominator because of the negative power. So this is 2 over the square root of x. So there's the derivative of this guy. All right, so I think this is probably what they intended. I'm hoping, Aaliyah, that all that happened is that you miswrote it as you were transferring it from the computer. But if not, let's look at how we could actually calculate this one.
I think I did write it down right, but I think maybe they had also said to do it the other way, and I was just trying to figure it out with our new rules.
Okay. Yeah, because this one now, I mean, I can tell you what it is because I know the trick, right? I know the chain rule. But if you were going to do this with what we've got so far, we'd have to use that limit definition. So we're going to do the limit as h goes to 0 of f of x plus h minus f of x all over h. Right, so we're going to use this. So if you were to plug the x plus h in, you're going to get 4 square roots of x plus h minus 6 minus 4 square roots of x minus 6 all over h. And still we're taking our limit as h goes to 0. Now for this one, we're going to have to rationalize, and this one gets kind of ugly, but we're going to multiply top and bottom by the conjugate, and the conjugate here would be 4 square root of x plus h minus 6 plus 4 square roots of x minus 6. And so again, we need the same thing on the bottom. Oops. It's minus 6. Sorry about that. Okay, so I'm going to erase this stuff over here so we've got some space to write. So now we get to do that multiplication. So on top, it ends up being a difference of squares. So we're left with the limit. So limit is h goes to 0 of, we're going to get 16 times x plus h minus 6 minus 16 times x minus 6. Okay, so if you FOIL that out, this is what you're going to get on top. On the bottom, we've got h times, and I'm just going to leave that big expression as it is. I'm not going to try to simplify or multiply through or anything. And now on top, a bunch of stuff's going to cancel because we're going to get 16x minus 16x. We're going to get 16h, so there's 16h. 16 times 6 is 96, so we get minus 96 plus 96, so that's all gone. And so on the top, that simplifies down to just 16h. All right, so now I can cancel those h's. And we're ready to do our limit. So on top, we're going to get 16. On the bottom, I'm going to get 4 square roots of x minus 6 plus 4 square roots of x minus 6. Right, because when the h goes to 0, it just leaves us x minus 6. So that's 16 over 8 square roots of x minus 6. And then the 16 and the 8 reduce. So we're left with just a 2 over the square root of x minus 6. Whew. So we can do it. It's just we have to attack it using the limit definition. But soon, very soon, as in most likely Monday, we're going to learn the trick for this one. We have to use what's called the chain rule, and the chain rule deals with composition, because you notice here we've got composition. We've got another function, x minus 6, that's being put into a square root. And so since there's a rule for everything else with derivatives, there's also a rule for composition of functions. And so once we've got that, we'll see the fast way to go from 4 square roots of x minus 6 to 2 over the square root of x minus 6. Anyway, so is that better for this one?
Yeah, thank you.
Yeah, all right, you're welcome. Okay, so let's go take a peek at those other ones from section 3.3. So let me share that screen. While I'm here, you can probably see how the due dates got swapped. So just watch for that. we have a chance to talk about it on Monday again if there's an issue. But okay, so while I'm waiting for this, here's a really bad joke of the day. So we have a railroad museum in Carson City, Nevada, and I volunteer there. We operate like steam locomotives from the turn of the century, and I mean like 19th to 20th century. So anyway, so I play around on trains, and one of the things I do is I talk with people a lot. So of course I have really bad train jokes. So here's your bad train joke for the day. What do you call a railroad worker who's been struck by lightning? A conductor. That's okay, you can drown. They are bad.
I enjoyed it.
You don't have to brown nose me, but I appreciate it. No, that's one of those that the kids, they laugh, they don't really get it. The parents, they get it, and they groan a lot. That's usually oh my god. And the best is when I'm actually conductor on the train and I tell that joke. So, all right, so I think we've got enough time here. So it was 11 and 14, if I recall correctly. So let's go take a peek at number 11. All right, so here's what we've got. It says we've got a function that's x to the 10th times h of x. And I think, Susanna, you said yours was like x to the 7th or something like that, but it's going to be similar to this, right? But then we're also told that at -1, h is equal to 2, and h prime is equal to 5. And we want to calculate f prime. Now, this is something that you said earlier, Susanna, and I just want to make sure that it was just a misstatement. This is not asking us to do anything with the inverse. Remember this notation.
Oh, I was thinking derivative.
Yeah,
Sorry.
okay. No, and that's what I figured. I figured it was just a misspeak because, you know, when we write inverses, we write that -1 up there. But it is kind of important that there's a big difference here, right? So we are trying to find the derivative.
F prime, right?
Yeah. So we're trying to find the derivative.
Okay.
All right. I figured that was just a misspeak, so no worries. Just want to make sure we're all on board with this. All right, so now let's see if we can figure out the derivative at -1. Okay, so I'm going to share my whiteboard again. Let me clear all that. All right, so what we had was that f of x was equal to x to the 10th times h of x. Now, here's what I want to do first. Let's get the derivative of this guy. Now, they did give us a hint. They said use the power rule and the product rule. But you should be able to see why we need to use both of those. First of all, product rule. I've got two things that are being multiplied together. So that's just screaming, use product rule. Okay, so let's think about product rule. We take our two functions and we find both of their derivatives. Okay, so the derivative of x to the 10th, we can use the power rule, and that's going to give us 10x to the 9th. Exponent comes out front as multiple, decrease the exponent by 1. Right? And then we need to differentiate h. Now, I don't have a rule. I mean, I don't have a function here, like an equation for it, but I'm just going to write, okay, so it's h prime of x. So now the product rule says multiply one times the derivative of the other and then add them together. So this is going to give me 10x to the 9th times h of x plus x to the 10th times h prime of x. So if we actually knew what h of x was, if we were told, right, h of x is this function, we would put that right here. We put its derivative right there, and we'd be good. All right, so far so good. Which is our derivative, I hope. All right.
Yes,
now,
this is where I got confused.
Okay, so now let's look
When
at
I
what
was plugging it in, I think is what
Good.
happened.
Okay, but you're right. We do need to plug this in. We're going to plug in -1. So let's just do this. So we're going to get 10 times -1 to the 9th times h of -1 plus -1 to the 10th times h prime of -1. So I just put -1 in everywhere there's an x because that's what it's telling me to do. And some of this we can just calculate, right? The -1 to the 9th times 10, we can get the number for that. -1 to the 10th, we can get the number for that. But we've got these two, the h of -1 and the h prime of -1. We need to know those values. But luckily, they gave them to us, right? In that list, they told us that h of -1 was equal to 2. And we were told that h prime of -1 was equal to 5. Again, your specific problem may have different numbers there, but they told us this, right? They said that h of -1 was 2, h prime of -1 was 5. And now I have just numbers, and I can do all of this. So -1 to the 9 is going to be -1. The fast way of dealing with this is just look at the exponent. If the exponent is even, it's positive. If it's odd, it's negative. So -1 to the 9th is -1 times 10 times 2 is -20. And then I'm going to add to that. -1 to the 10th is 1. 1 times 5 is 5. So -20 plus 5 is -15. So we should be able to put that into the box, get our green check mark, get our point, and life will be good. So notice that we didn't actually need to know what the function was. We just needed to know the function's value and the derivative's value. That was sufficient for us to be able to figure this out. All right, so does that make a little bit more sense with this one?
Yes, thank you.
All right, you're welcome. Okay, let me switch sharing again here, and we'll go back to the homework set. And we'll go look at number 14.
Yeah, 14, my example, they gave me something that was a half. Like the derivative landed on a half. It wasn't a full number.
Okay.
So I wasn't sure if I just got the decimal point wrong.
All right. So did yours look something like this?
Yeah.
Okay. Well, let's see what we can do here. And if we end up at a half, we end up at a half. If not, I'll give you my best guess of how to do this. But here are two functions. We've got g and we've got h. Now, we could figure out the equations for these, right? G, since it's a line, we just find 2 points, get the slope and all that stuff. We could find the equation. This one, since it's an absolute value, we could probably do the same. But it turns out we don't really need to know that because we're told that F is the ratio of them, of G and H. And so we want to find F prime of 3. All right, now I'm going to go to the whiteboard, but then we'll come back to this picture because we definitely need it. I'm not smart enough with this guy to actually kind of show you both at the same time. I'm sure there's a way, I just don't know it yet. So we're just gonna have to deal with this. All right, so what we were told is that we've got a function that's equal to g over h. and we wanted to find f prime of 3. So that means we need the derivative, and then we need to plug in 3. Now, this one's a quotient rule. Got one function divided by the other. So to do quotient rule, again, we need the derivatives of both of these. Okay, well, they're unknown functions, so the derivatives are the derivatives. But then we do our little cross multiplication trick here to get our derivative of f. And so f prime is going to equal g prime times h minus g times h prime divided by h squared. So this is that general formula. Again, there are two ways that I showed you to remember. One is with the little rhyme that goes low d high minus high d low, square the bottom, and away you go, right? Or how I told you I remember this is by looking at these lines. The one with the positive slope is the positive piece on top. The one with the negative slope is the one with the negative piece on top. And again, square the bottom. But regardless, however you get there, there's our derivative. So if we're going to do this at 3, just like before, we're just going to plug in all these 3's. Okay, so looking at this formula, look at what we need to know. We need to know g of 3 and h of 3. So we actually need to know the function values at 3, right? That'll take care of those 3 pieces. But then we also need to know the derivatives of g and h at 3, which means we need to know the slopes of the tangent lines at 3. Okay, so there's what we need to figure out. So let's go back to the graph. So let me switch it again, because the graph is going to be where we get all this information. Okay, so remember some things that we need to define. First of all, we need to know g of 3, and we need to know h of 3. So on the graph of this, g of 3, we're going to look at 3. We're going to run up to this point right there, and we're going to see that that y value is 6. So g of 3 is equal to 6. So I'm just going to write that down on a piece of paper here, but I got g of 3 is 6. And then I can do similar thing to get h of 3. So again, we're going to come back here. Here's 3. And we run up here, h of 3, and it definitely looks like it's 4.5. Okay, so we can go with 4.5. So let's just see what happens there. So g of 3 is 4.5. Now, how confident are you that it's 4.5? That's a legit question. What do you guys
Well,
think?
yesterday I was like 95% sure, but then I got it wrong.
Okay, and so now you're maybe a little bit lower. All right.
Sure,
Well,
92%.
okay, so here's what I would do. I would actually look at this thing and think about the slope, right? And so basically, if I were to go here, I've gone over a half and down a half. Does that look like that continues? Over a half, down a half, over a half, down a half, over a half, down a half. It seems like we're pretty good. So if it's not 4.5, it's awfully close. So we'll go with 4.5 and we'll see how that goes. All right, so there then are g of 3 and our h of 3. Right, g of 3 was 6. H of 3 was 4.5. Okay, but now we also need g prime of 3 and h prime of 3. So that means we need to know the derivatives at these points. So thinking about this one, let's look at G first. We need the tangent line at x equals 3. Well, since the graph itself is a line, the tangent line is that line. So what we need is the slope of this line. So what's the slope of G?
Is it 2?
It is 2. You can see we go up 2 over 1, right, from any point. Up 2 over 1, up 2 over 1, up 2 over 1. So we've got G prime of 3 is 2. That's the slope there. So you're going to like lines when it comes to finding derivatives because the derivative is the slope of that line. Okay, so let's go to H. So same story, but now we're over here. And we want to know what is its slope. Okay, well, again, at this point, we're on a line. So the tangent line is this line, the piece of the absolute value that's over here on the right. So the question is, what is that slope? So someone just threw something into the chat, but I can't see it. Ugh, I just lost everything. Hold on here a second. All right, so Errors just said -1. Thank you. Sorry about this, guys. I hit the wrong thing. Okay, so I agree. I think the slope is -1. Because again, remember when I was kind of talking about it, I'm going down a half over a half, down a half over a half. I'm going down as much as I am going over. So I think that that guy is -1. So that's what I'm going to go with. That this derivative right here is -1. And the derivative of G was +2. Okay, so let's go back to the whiteboard. And let's put those numbers in. Okay, so this is what we saw looking at the graph. We saw that G of 3 was 6. H of 3 looks like it was 4.5. We had G prime of 3 was 2. And H prime of 3 was -1. So let's put all of those into this guy. So we got G prime of 3, that's 2. H of 3 was 4.5. G of 3 was 6. H prime of 3 was -1. And H of 3 was 4.5. And we're going to square that. All right, so now it's just a matter of doing the numbers. So 2 times 4.5 is 9. -6 times -1 is +6. So 9 plus 6 is 15. And that's going to be over 4.5 squared. So that should be 20.25, I believe. Definitely check me on that, though. Let's see. I know 15 actually goes into this. So 15 goes into that. 1 point. No. 12, 13.5. 1.35. I think. Whatever. This is what it is. And so this is the number that we're going to put in to our thing. So let's see if our answer is actually correct. So I'll go back. If someone could actually get me a decimal for that, that would be awesome.
0.7407407407.
So 0.74 with the bar over it.
Yeah.
Okay, cool, thank you. All right, so let's go see if we got that right, or if the computer agrees that we got that right. Okay, so I'm just going to put 0. Actually, I'm going to put it as a fraction. If it's 0.74 repeated, that's the same as 74/99. So let's see what that does for us. Cross your fingers. Oh, what? All right. Well, let's just see what it says. No, it doesn't do what I want it to do. All right. So I'm not sure why that didn't like that number. Maybe it did want it as a decimal, but that's definitely the right process. So what I'm going to tell you, like Susanna, since you said you thought you did it right and it didn't give you the right answer, send me a message with that number, and I'll look at your specific homework. And if I agree that what you did was proper, then I will give you the points. All right.
Okay, I'll retry sometime.
Okay. Anyway, yeah, I don't know why that didn't like it, but that was definitely the process that we need to do. Anyway, I'm not gonna lie, today felt like a Monday from the start, so I'm not surprised that this happened because this usually happens on Mondays. Anyway, all right, so better for that one-ish. It would have been way better if we'd gotten the green check mark and not the red X of shame. All right, so any other questions on homework before we move along? All right, hearing none and seeing none. I'm going to go ahead and hop to the whiteboard, and I'm going to just real quick talk a little bit about the quiz, and then we're going to do some trig derivatives. All right, so I will see you guys in just 1 second. All righty. So first, let me go ahead and go over the quiz just so you can see the approach and what you needed to do. And like I said, if yours hasn't come back yet, I'm not quite done grading all of them, but it'll happen later today, I'm sure. But the first one, this was just evaluating a limit. So we had the limit as x approaches 9 of 3 minus the square root of x over x squared minus 81. And so just about everybody saw what we needed to do to start, which was to multiply by the conjugate. You want to rationalize this thing, so we're going to multiply top and bottom by 3 plus root x. So on top, we're going to get 9 minus x. On the bottom, we still have x squared minus 81 times 3 plus root x. But for this one, the trick is we need to factor the bottom. X squared minus 1, if we factor that, will give us an x minus 9 and an x plus 9. And that's going to make it so that we can actually simplify this thing, because now the x minus 9 and the 9 minus x, those will cancel, but leave behind a -1. Since their signs are opposites, you can factor out a -1. So this is the limit as x goes to 9 of -1 over x plus 9 times 3 plus root x. And now it's just a matter of plugging in the 9 so that we get 18 times 6, since the square root of 9 is 3. 3 plus root of 6. So you can go ahead and multiply those out and you get negative 1 over 108. So like I said, the ones I've graded so far, most people saw that you did need to rationalize this. It's just then we got a factor. So that was number 1A. Number 1B, and again, I apologize for the typo on this. Some of you caught it. It said the limit is t goes to -1. It was supposed to be an x goes to -1. But this is one that we just need to factor. So we've had 3x squared plus 5x plus 2 on top. And on the bottom, we've got x squared minus 5x minus 6. All right, so if you factor this, you get on top 3x plus 2 times x plus 1. And on the bottom, you get x minus 6, x plus 1. So those x plus 1s cancel. Let me jump down below the reflection here. So we get the limit as x goes to -1 then of 3x plus 2 over x minus 6. And now this guy we can just plug in. So we get -3 plus 2 over -1 minus 6, which is -1 over -7, or 1/7. But this is another one, most of you saw what you needed to do. Okay, so then on the back page, this is the one where I gave you a graph and just said list all the discontinuities and talk about other stuff. So first of all, the discontinuities, I know if you don't have it in front of you, this doesn't really help, but you can always re-watch this video. The discontinuities are at -8, -2, 6, and I believe that's it. And then I asked which of those are removable, and it turns out that the only one that's removable is at -8. Removable, those are the ones that basically you can fix by just plugging your finger in, right? So holes, or the holes that have like a dot above it. But the other ones with jumps and infinity, those are not removable. So the only one that is removable was at x equals -8. And then I asked you to evaluate a limit. And this one was the limit as we approach 6 from the left. And that's actually equal to 2. So when you look at that graph coming from the left, it approaches 2. From the right, it approaches like 5 or something like that. But since it was just a left-sided limit, it's 2. The one thing I do want to mention about that, some of you saw that as a limit as we approach -6. Remember, when it's up as an exponent, that's either telling you left or right. Anyway, so there's the quiz. And like I said, for those of you who don't quite have it yet, it'll show up in your thing later today, hopefully. Right. Okay, so there's the quiz. All right, so what I want to do today is I want to actually finish off getting you trig derivatives. There are the 4 functions, right? Or sorry, 6 functions: sine, cosine, secant, cosecant, tangent, cotangent. And we already have 2 of them. We've already done 2. We got sine and we got cosine. So what I want to do is develop the other 4 so that we've got them all. And in the process of this, it will help us practice some of the other rules. Quotient rule, product rule, all that. So we'll kind of keep refreshing those things as we go. But in order to do this, let me remind you about sine and cosine. So we'll go ahead and start making a list here of the derivatives that we know. So let's make a little chart here. F of x and f prime of x. So sine of x, we saw a while ago that its derivative was cosine. So we actually proved that using the limit definition. Had to use some trig identities and all that, but it got us a derivative of sine is cosine. And similarly, we saw that the derivative of cosine was negative sine. All right, so we already have those two, and what I want is to get a list of the others. So this is what we're going to fill in today. We're going to fill in these other 4 slots so that we've got all 6 trig functions derivatives.
Can I ask a quick question?
Sure.
I was just looking, I remember that you had said that there's a resource posted somewhere with the trig identities, and I just wasn't able to find that on the site. Do you know what link that's under?
Yeah, so on the side, you know when you get into Canvas, you've got a menu that's on the side
Uh-huh.
that has like, you know, assignments and whatever. There's one that says files.
Okay.
So if you go to files, it'll bring up the files for this class, and in there I put a folder that says like trig review or trig, something like that. And in that folder, there's a list of identities, a sheet of identities, and also a sheet of all the special angles.
Great. Okay, I see that. Thank you.
And then trig values. So yeah, so you find it under files, and then you should be able to get there. If you're still having trouble finding it, let me know. I can always just send you those files directly.
Great. Thank you.
But you should be able to get them through Canvas. All right, so we want to develop the trig function, the derivatives for the rest of these guys. All right, well, here's what we're going to do. We're going to use the fact that all these other 4 are built out of sine and cosine. Okay, we know that that's the case. And so, for example, let's look at secant. So secant, how is that related to sine and cosine?
1 over cosine.
Okay, so it's 1 over cosine. So what this is going to let us do then is actually use the quotient rule. This is one function divided by another. Yeah, I know it doesn't seem like it because 1 doesn't really seem like much of a function, but it is. Constant function. So we're going to be able to do the quotient rule on this. All right, so here are our 2 functions. The one on top is 1. The one on the bottom is cosine. So let's do the quotient rule. Let's get their derivatives. So the derivative of cosine we know is minus sine. Right, it's on our list over there. What's the derivative of 1? All right, good. It's 0. There's just put in the chat box because it's a constant function. So for the quotient rule, let's put this together the way that we need to. So we're going to get on top for f prime 0 times cosine of x minus 1 times negative sine of x. And we're going to divide by the bottom squared. So good old quotient rule. Low d high minus high d low, square the bottom, away you go. All right, so let's simplify this a little bit. So 0 times cosine, of course, is 0. Negative 1 times negative sine is a positive sine. So we get sine of x over cosine squared. All right, so there is the derivative of secant. but you'll never see it written this way. What we end up doing with this one is we turn it back into the trig functions, into the other trig functions. So I'm going to split this. I'm going to make this 1 over cosine times sine over cosine. And each of these is another trig function. The 1 over cosine, that's secant, right? That's what we just started with. And what's sine over cosine? Which trig function is that?
Tangent.
That's tangent. Good. All right, so this is how we're going to remember the derivative of secant. The derivative of secant is secant times tangent. And trust me, this is way nicer than trying to use the limit definition, which then would involve sum of angles inside of a secant, which that gets horrible fast. This is quick. But kind of interesting, actually, that the derivative of secant still gives us other trig functions, including the secant itself, right? Its derivative is related to itself. Fun fact. All right, so good for this one. There's your derivative of secant. So we're going to do all the rest in kind of a similar manner. But the next one I want to look at is cosecant. Because how is cosecant based on the sine and cosine? Anyone remember?
Cosecant is 1 over sine.
It's 1 over sine. Yeah, so if we do the same thing, though, this is now going to be 1 over sine. So we're just going to do the quotient rule again. We just have different functions on the bottom, right? The top is still 1, the bottom is sine. So now when we differentiate, the derivative of 1 is 0, and the derivative of sine is cosine. We do our little cross multiply thing, and so what we get is the derivative of this thing is going to be 0 times sine minus 1 times cosine all over sine squared. So we'll simplify like we did before. So we get negative cosine over sine squared, which we'll split up again. We'll make it negative 1 over sine times cosine over sine. So 1 over sine is cosecant. Now what's cosine over sine?
Cotangent.
It's cotangent. All right, so this is what we're going to remember for the derivative of cosecant. It's negative cosecant times cotangent. All right, so look at that. We are now 2/3 of the way done with the trig functions. We've got 4 of them. Before we hit tangent and cotangent, I do want you to notice that there's a similarity here between secant and cosecant. Right? The structures are very similar. We just have the co-functions instead, right? So instead of secant, there's cosecant. Instead of tangent, there's cotangent. So very similar structure, just co-functions, and the one is negative. All right, well, there's secant and cosecant. All right, well, that leaves tangent and cotangent. And we're just going to do exactly what we did here, except use the identities for tangent and cotangent. So let's look at tangent. How do you build that out of sine and cosine?
Sine over cosine.
Good, so it's sine over cosine. And so now when we do the quotient rule, those are the two functions that we're differentiating. So the top is sine, the bottom is cosine. Their derivatives respectively are cosine and negative sine. So we'll do our little cross multiply. So we get the derivative of this is cosine times cosine minus sine times negative sine. And that's all over cosine squared. So on top, we get cosine squared plus sine squared over cosine squared. And now to simplify this, we'll use the Pythagorean identity. Cosine squared plus sine squared is 1. This is 1 over cosine squared. But we're going to go ahead and turn those back into trig functions. 1 over cosine is the same as secant. So this is the same as secant squared. All right, so the derivative of tangent is secant squared. If this looks familiar, it should. I did this example at the very end of class last time. I didn't tell you we were differentiating tangent. I use this as an example of doing quotient rule. Oh, right, sneaky math teachers. So we did this. We went at least as far as 1 over cosine squared. But there is the derivative of tangent. Okay, before we get cotangent, I just want to point something else out. I love trig, by the way. If you don't know this about me, like, I'm crazy about trig. I love it. It's my favorite class to teach. I see the beauty in it. And like, this is one of the reasons why I love trig, is you see the interconnectedness between all of these seemingly random functions. I mean, yeah, they all do come from a right triangle definition or unit circle, whatever, but there's so many relationships between them. And this one, I mean, check this out. So tangent, its derivative is secant squared. Tangent and secant are already kind of connected. If you look at the Pythagorean identity, the one that involves tangent, it has secant as well. It says tangent squared plus 1 is equal to secant squared. And so they're already really connected. The derivatives show that even more. Just like sine and cosine are connected, I mean, they're really the same graph, they're just shifted. And you see that even here in their derivatives, right? So every step I've ever taken further in math that then relates back to trig just sort of strengthens my love of it, my appreciation of it, because there are so many patterns that involve them. But I know most of you don't care about trig. I'll work on changing that, but yeah, it's kind of beautiful. All right, so there's tangent. Now, we're going to go ahead and develop cotangent's derivative. But think about the patterns that we're seeing here. Look at what happened with sine and cosine and with secant and cosecant. They were similar. They just had their co-functions, right? And cosine's derivative was negative, cosecant's derivative was negative. So if that pattern follows, here's going to be my guess of what we should get for cotangent. Okay, so this is a guess. Is that it should be negative, to go with the fact that these other guys are negative. And I should have the co-function instead of secant. That would mean I get cosecant. So this is my guess. If we just look at the patterns, let's see if that pattern holds up. All right, so if we go to cotangent, we'll start the same way. Cotangent It is cosine over sine. So if we build our derivative here, on top is cosine, on the bottom is sine. Their derivatives are negative sine and cosine respectively. So let's do the quotient rule. So we're going to get f prime of x is equal to cosine times cosine, or sorry, minus sine times sine, minus cosine times cosine over sine squared. So this is negative sine squared minus cosine squared over sine squared. All right, well, this guy, minus sine squared minus cosine squared, is actually equal to -1. Again, sine squared plus cosine squared is equal to 1, so it's -1 over sine squared. And 1 over sine is cosecant. So notice that we did get negative cosecant squared. So in terms of memorizing these, because again, it all comes down to being able to remember this stuff. Notice that you don't actually have to learn all of them. You only have to learn sine, tangent, and secant. Because if you know those three, the other three are just opposite in signs, so they're negatives. And then you just use the cofunction. So turns out it's actually not that bad. But there's a lot of interrelationship between them. All right, well, now you've got all of the trig functions. So think about what you can differentiate right now, what we have rules for. You're good for any kind of a polynomial, any kind of a trig function. You're good with radicals as long as there's not stuff inside the radical, right? Think about that one that Leah asked about earlier today, right? So there's plain old radicals, we got those. Fractions, we're good with fractions as long as we can differentiate top and bottom. You're good with anything that you multiply together. I mean, we're getting them fast, right? There are lots of things we can do now. There clearly are some we can't do yet. We haven't talked about exponential functions, logarithmic functions. We haven't talked about what do you do when you do have composition, right? Like the square root of x plus 6. So we still have more things to develop, but we're getting there. And they're going to come fast now because we learn these processes. We're learning these processes that make it go a lot quicker. So why don't we just do a couple more with trig just to kind of play around with them. And then we'll turn our attention to the exam. So let's do some higher order derivatives. That's probably some good practice because we really haven't done much of that yet. I introduced them to you, but we really didn't do anything because we didn't have the rules yet, and I didn't want to do higher order derivatives when I didn't have the rules. So now that we've got these rules, let's do higher order derivatives, just so you can see kind of the process. So let's actually take, say, sine. We'll start with sine. I think this is going to be easiest. So let's say we've got f of x equals sine. So let's start finding some higher order derivatives. Now, the first derivative we already know is cosine. So let's find the second derivative. So remember what second derivative means. That means take the derivative of the derivative. So we're going to differentiate f prime. Well, f prime was cosine, and so its derivative is negative sine. So this is kind of funky. Here's a function whose second derivative is just the opposite of it. Well, let's keep going. Let's get a third derivative. So a third derivative means differentiate the second derivative. So we need to differentiate negative sine. All right, well, first, that negative is a constant multiple. It's -1 times sine. So that -1 is going to come along for the ride. But then we need to multiply by the derivative of sine. Well, the derivative of sine was cosine. So this ends up being negative cosine of x. All right, so there's the third derivative. Let's go to the fourth derivative. Now, like I told you, the fourth derivative and beyond, they're very rarely used. In fact, we barely go past the second derivative, but I mean, we can just keep differentiating. But let's see what we get here. So now we're going to differentiate negative cosine. Well, the negative is a constant multiple, so -1. And then I need to multiply by the derivative of cosine. Well, the derivative of cosine was negative sine. Negative, negative makes that a plus. And so the fourth derivative of sine is sine. Well, what if I ask you to get a fifth derivative? Now it's going to be cosine. And then the sixth derivative, negative sine. Seventh derivative, negative cosine. Eighth derivative, sine. And we're into a cycle, right? Like, look at what we started with, sine, turned into a cosine, which then became a minus sine, which turned into a minus cosine, which turned back into a sine. And now if we differentiate, we're just going to fall into that pattern. So sine is kind of interesting, that if you just keep differentiating, you end up going through a cycle. You keep rotating through those four elements. And the beautiful thing about cosine is it does exactly the same thing. We just start at a different stage, right? But we start at cosine, then we go minus sine, then minus cosine, then sine. But its fourth derivative is going to be cosine. Another beautiful thing about these functions. When you differentiate them, they just repeat. Okay, well, fun fact. We'll see other functions that do similar, where when you differentiate, you end up running into the same thing again. It's rare. It's not very common. Most functions don't do that. In fact, let's tackle, say, like secant, and let's see what happens when we differentiate it more. All right, but before I do that, we good on this one? Any questions? All right, so how about we do the same thing for secant? So we'll start with f of x is secant of x. Let's find some higher order derivatives. So the first derivative, we just calculated it, we found is actually equal to secant tangent. All right, so let's get the second derivative then. So how are we going to differentiate secant tangent? What rule are we going to use? And this is when I start questioning if anybody's actually out there. All right, thanks, Bailey. So we want the product rule, because we're multiplying secant times tangent. All right, so we've got secant, we've got tangent. Let's look at what their derivatives are. So secant's derivative is secant tangent, and tangent's derivative is secant squared. All right, so we put this together. We're going to get f double prime is secant tangent times tangent plus secant times secant squared. So this is secant tangent squared plus secant cubed. Okay, so unlike sine and cosine, notice that we start doing higher order derivatives here, and they start getting ugly, right? We started with just secant. That was beautiful. Turned into secant tangent. Not a big deal. That's derivative is secant tangent squared plus secant cubed. And probably at about this point, you go, yeah, thanks, no thanks. I don't want to go any further, right? And we won't. I mean, we could do a third derivative on this, but it's going to be super long and messy and no point in going anymore. All right, but higher order derivatives, I mean, we approach them the same way. It's just now we can use our rules. All right, so we'll stop this one here, but I do want to do one more. I want to show you how we would tackle, say, tangent, doing the same kind of idea. So let's just do that down here. So let's do the same thing for tangent. So we know its first derivative is secant squared. So the question is, how do we find the derivative of that? Well, you might see this secant squared and go, I have no idea how to deal with that power because it's not just x squared or whatever. But think about it this way. Think of it as secant times secant. And so since it's secant times secant, we can use the product rule. All right, so let's do that. So we've got secant and secant are our two functions. So we need their derivatives. Well, both of them are secant tangent. So we'll do our little cross multiply business here. And we end up with f double prime is equal to secant tangent times secant plus secant times secant tangent. Notice that these are identical. So when I put them together, I'm going to get 2 secant squared tangent. So tangent, its derivative was secant squared, and its second derivative is 2 secant squared tangent. And if we felt so inclined, yeah, we could continue. Do it again, do it again, do it again. Right. All right, so there are the trig functions. So like I said, we're kind of going a little bit out of order in the book. This is 3.5. We'll come back, we'll talk about 3.4 next time. Anyway, all right, so there are your 6 trig functions with their derivatives. And now you're equipped to do anything with trig. Yay. All right, so any questions on any of this before we start talking about the exam? No? Okie dokie. All right. So we got about 25 minutes left, which would be a good time for us to sort of bring back ideas that you're going to need to know for the exam, what you should do, how to prepare, and so on. So let me just start here in terms of the topics that the exam is going to cover. So we'll kind of just make a little outline and talk about what you should expect to see what kind of topics there are. So exam 1 is on Friday. And so we're not having class. There will be no Zoom session. You're doing the exam instead. So think about if this class was going on in person, that's what we'd be doing, right? We'd be sitting in the classroom, you'd take your exam, and when you're done with it, you'd hand it in to me, and then you'd walk away and be done. All right, well, we're going to replicate that. So instead of having a Zoom session, you're going to be online, you'll download the exam, do it, and that's it. Okay, so exams Friday. It is available at 8:30. So just like with the quizzes, it's going to turn on at 8:30. So if you get in there at 8:28, it'll still be locked. At 8:30, you're going to be able to grab it and start working on it. Okay, so it's available at 8:30, but it needs to be submitted. I believe it's 11 a.m. is what I said on the syllabus and what I put in the Canvas. I'll make sure of that, but I'm pretty sure it's 11 a.m. So basically, here's how to think about it. It's a 2-hour exam. If we were in class, I would give you 2 hours for it. I would bring that to 10:30. I'm giving you extra time just to deal with technology issues. Okay. You need to upload these on Canvas. I will not accept any that are not uploaded on Canvas. All right, I let people slide on the quizzes because I know it's kind of new to us and everything, but by now you should have figured out how to put it up on Canvas. If you still don't know how to do that, reach out to me, okay? But they need to be submitted through Canvas because exams are bigger. It's a lot more difficult for me to try to find them in emails and all of this, that, and the other thing. So they need to be submitted in Canvas. That's why I give you that extra half hour. Okay, so I'm giving you extra time to deal with that aspect. So I'm going to have zero sympathy for the people that are like, well, I tried to upload it and I ran out of time. Like, well, that's because you weren't doing it soon enough, right? Like, honestly, you should be uploading it at 10:30. Gives you half an hour to figure out, oh no, there's bullshit going on, I can't get it done, right? So and I'll be on my computer, I'll be checking emails and messages so that if like at 10:45, you're saying, man, I'm trying to upload it and I'm having trouble, there's still time for us to figure it out. You send me that email at 10:58, it's not going to work. Okay, so you understand the idea here? I'm not giving you 2.5 hours for the test. I'm giving you 2 hours for the test and a half an hour to figure out all the tech issues. Okay, so make sure it gets uploaded in Canvas. I know most of you are not, this doesn't apply to most of you, but just we're uploading it on Canvas. All right, so in terms of what it's going to cover, all right, it's going to cover chapter 2. So all of chapter 2 and sections 3.1 and 3.2. So first of all, notice it doesn't say anything about chapter 1. Chapter 1 was all that review of pre-calc, and I'm not going to test you on that specifically. Do you need to know how to do it? Yes. You need to know how to factor. You need to know how to rationalize. You need to know how to find lines. You need to know how to do all that stuff. But I'm not going to specifically ask you about it. Okay. So technically, this covers chapters 2 and sections 3.1 and 3.2. But obviously, you need to know your pre-calc algebra trig stuff to be able to do these later sections. All right. So what are those topics? What does this actually entail? All right. Well, chapter 2 was all about limits and continuity. So let's just start with limits. Things that you should be able to do. You should be able to deal with these in all 3 different ways, right? We had 3 different ways of doing limits. There was graphical. So if there's a picture, you can kind of follow along and find your limit. There's numerical. Plug in numbers that are near the point and see what kind of pattern you get. And then there's algebraic. Do the factoring, do the rationalizing, and so on. So know all 3 of those. So numerical, graphical, and algebraic. Okay, so know how to evaluate limits. Understand the idea behind limits, what they mean, what they do. All right, so know the limits. Other things that you should know about limits. You should definitely understand one-sided limits. What that means, looking at it coming from the left or from the right, from smaller numbers or from bigger numbers, and the fact that they have to be the same for the limit to exist. Okay, so know about one-sided limits. And then also, I'm going to put here epsilon delta. So that was that precise definition of the limits. You should know how that works. You should be able to, if I were to give you an epsilon for a specific function, you should be able to give me a delta that works, right? So go back and look at those. Trust me, when I put one of these on here, I'm not going to make anything really horrible. Like I'm not going to give you epsilon delta for a trig function, right? Or an exponential or something like that, where I expect you to do the algebra on it. If I expect you to do algebra on it, it's going to be nice. It's going to be a line, maybe a quadratic. So just realize that. So Leah just put in the chat, is the exam open note, open book? The answer to that is yes. Since you're taking it at home, I can't really police that anyway, and I don't want to police that. So yeah, it's open note, open book. Realize that that does come with a consequence, right? Like an exam that you guys are going to get in this format is going to be a little bit more difficult than one that would be in class, because I know you have those resources. Okay, so open notes, open book is fine. What is not fine is using some other site to actually do the math for you. You know what I mean? Find a site where you just type in a limit and it spits out the answer to the limit. That's not okay, but it is okay to reference your book, reference your notes. That's totally fine. And just so you guys know, I can tell. I can absolutely tell if you're using a resource that's not you. All right. Which is one of those things, because I've been doing calculus forever and I've been teaching calculus forever. I've seen it all. And so when I see something that is completely different, I know it's not you. All right. So please don't do that. Right. And I don't really think I need to preach to you guys so much, because most people don't take calculus just to check a box. Right. If this was just this is the last math class you're ever going to take and you just need to do it, we might have to talk more about that. But you guys know that you need this material. You need to know this. So as you go further, you can understand other things. If you don't realize that, let me just tell you, because as a physics teacher, if you don't know this stuff, physics is going to be so much harder. So learn this stuff. Right? Anyway. Plus, it's just an exam. We obsess over grades for some reason. I don't get it. Anyway, so epsilon delta, yeah, know about it, know how it works, and be able to replicate it. Okay, so that's the idea behind the limits. One other thing I want to put on here, just because we did end up using it, I'm going to put actually two more things. One, I'm going to put the squeeze theorem. So that was the one when you've got two functions, one's bigger and one's smaller than the function you're looking at. And if those two functions come to the same point, then your function gets forced to that point. That's a squeeze theorem. And we actually use that for some of the trig limits. So I'm going to put those on here as well, the trig limits. And specifically, I'm talking about the limit as x goes to 0 of sine x over x, and the limit as x goes to 0 of 1 minus cosine of x over x. And those were equal to 1 and 0 respectively. All right, so that's basically chapter 2's contents. It's limits. Right? Oh, actually, that's not quite true. There's another little piece of it. So we had limits. The other thing that was in there was continuity. Let me put that on here as well. So remember what continuity is. There's the non-mathy way of saying it. You can draw the graph without lifting your pencil. But know the math definition for continuity. Look over here, definition. And that was the thing that had three pieces to it. the function had to exist. The limit exists. And then the third was that the limit actually equals the function value. So that's what it technically means to be continuous, but all that put together basically goes to the, yeah, you can draw it without lifting your pencil. Okay, so there's your definition of continuity. So be able to determine if a function's continuous or not, be able to look at it with a graph, that sort of thing. And so the only other thing that we talked about, I think, with continuity that is kind of important was the intermediate value theorem. And that's the one that says if your function is continuous on an interval, and you look at the endpoints on the interval, then every y value between those shows up at least one place somewhere in that interval. Okay, so that was the intermediate value. Okay, so I'm pretty sure that's chapter 2. There might be some other little things, but this was the bulk of what we talked about there. All right, so then sections 3.1 and 3.2. So I guess this is going to be now the third little chunk for this exam. That's about the derivative. And we're kind of in the middle of derivatives. So let me just be really clear on what I'm expecting you're going to be able to do on the exam. Okay, so for derivatives, first and foremost, know the limit definition. And I'm actually going to put an S on there, limit definitions, because we saw it 2 different ways. And what I mean by these are, the first one's the limit as h goes to 0 of f of x plus h minus f of x over h. That's the one we've been using the most, and we've seen that the most recently. So that one probably is up there, and you kind of remember it. The other one was the limit as x goes to c of f of x minus f of c over x minus c. That was the other form. But both of them are doing the same thing. They're bringing 2 points, and they're bringing them closer together, right? So we're starting with a secant line, and it's approaching a tangent line. So the first one just saying, let the space between those 2 points go to 0. The second one is saying, let that second point go to the first point. They do the same thing. All right, so know your definitions, because I will ask you to do that. All right, there will be at least one of find the derivative of this function using the limit definition. While we're at it, let me just mention this. If I ask you to use the limit definition, use the limit definition. If you use the fast rules that we've been developing later, 0 points. Because that's not what I asked you to do. I asked you to do it with the limit definition. So read the questions carefully, because I will tell you what I want. All right? And always show your work. Always, always, always show your work. I don't like miracle answers, because miracle answers, those come from other places. Right? Show me your steps so I know how you're doing it. All right, so know your limit definition for the derivatives. Also, know what they're good for, right? And basically know this, that the derivative, that's the slope of the tangent line, which is also equal to the rate of change. And that's how we kind of started everything back in the day, was looking at, well, we're looking at rate of change, instantaneous rate of change, which meant we needed the slope of a tangent line, which then got us the derivative, right? So we can approximate the derivative by using a secant line, so the slope of a secant line, which gives us an average rate of change. But if we want instantaneous, then that's going to require the derivative. All right. Yeah, so in terms of a derivative, that's kind of where we are. 3.3 is where we start using the rules, and I don't want that to be part of this exam yet because I know you really haven't practiced the rules much yet. So I'm going to kind of leave it there. All right. I'm just grabbing my book here real quick to make sure I didn't miss anything, specifically from 3.1 and 3.2. So that's kind of where we are. Some things that you might want to be able to do specifically with the derivative, not only apply the limit definition and calculate it or to approximate rates of change, but be able to do this graphically, right? You've seen a bunch on your homework, including like there was that one today with the quotient rule where we had to look at the graphs to find slopes and stuff like that. Be able to use graphs to look at slopes of tangent lines. So maybe I'll put here graphs of derivatives. So that if you're given the graph of a function, you can still get an idea of what the graph of the derivative looks like. You can figure out where the derivative is equal to 0, horizontal tangent line, where the derivative is positive, places where the tangent lines are going up, derivative is negative, where it's going down, things like that. So know how to do it graphically, because most likely I'd be surprised if I didn't. I haven't written the exam yet, so I don't know. But I'd be surprised if I didn't give you something where here's a graph of a function, tell me some stuff about the derivative. I like those kind of problems. Okay, so this is what you're in store for exam 1. All right, so again, I just want to reinforce a couple things. Show me your steps. Explain what you're doing. Okay. Your work, not somebody else's work. Right? That, I mean, I'm just going to call it what it is. It's cheating. It's plagiarism. Right? It'd be the same as if you're writing an exam or writing a paper for English class and you go and you copy somebody else's. Right? That's exactly the same as typing something in the computer and say, solve this. Okay? So show your work, but make sure it's your work. Right? Also, make sure you upload it on the Canvas. So don't push that time. Do not push that time, right? Because in the classroom, it would be 2 hours is up, you're putting it in my hand and I'm walking out the door, or else you're not turning it in, right? So same kind of deal. Yeah, that's kind of where we are. So it looks like we have like 5 more minutes. If there are any specific questions you guys have, anything you want to look at, I'd be happy to do that. Or if we're good, we can just call it a day.
Are you going to have any acceleration questions?
Potentially. Potentially. I mean, acceleration really just gets at the higher order derivatives. And actually, let me put that on here because this, I guess that was another thing that we did talk about. But yeah, if I ask for acceleration, I'll probably even in there say, remember, acceleration is the rate of change in velocity. Trying to clue you in on that it's the derivative of velocity. So could that be there? Yep. Will it be there? I don't know. We'll see how I'm feeling as I write the exam.
I have 2 quick questions. One is just technical. Do you know if we go back to those old homework sets, can we still click like retake and do some practice problems?
I believe that you can, for no score, right? It doesn't change your score, but I believe that you can go in there and practice them.
Okay, great.
Yep.
And then
I believe that that's the case.
Also, one quick question about epsilon delta. I felt like I don't have a question in front of me right now, but it felt like they were like arranging those questions in a whole bunch of different ways than how we had gone over it in class when we were doing the homeworks. I think we went over a few of those before last class, maybe. But are you typically just going to give us the epsilon and then we'll give you like a delta that works? Is that the format, or should we be able to think about that in a lot of different setups?
Primarily, that is how it would go. I'd give you an epsilon, you give me a delta. So I might give you one where I give you a specific function and say, you know, given an epsilon of 0.1, what delta will work, you know, or something like that. So then you would give me a delta.
Okay.
But I could also just say, hey, you know, given a generic epsilon, how do you find the delta? And you have to kind of go through the steps. And so then, you know, when we do it algebraically, I go, oh, okay, so delta is equal to epsilon over 2, or, you know, whatever. So I could ask it like that. Because there are multiple ways of getting at it.
Yeah.
So I guess the long answer to your short question is, I don't know. I mean, yes, you should know how to do things with epsilon delta more than just, here's an epsilon, find a delta.
So if it's the generic epsilon, that's when you just put it into the equation as epsilon and then get out something else that you could plug in.
Yeah, you do the algebra. You do the absolute value of, you put your function minus the limit, and then you do algebra on it until this looks like x minus c. And then whatever's on the other side of the inequality, that's your delta.
Great.
All right, so it sounds like we're pretty much wrapped up. So good luck. Like I said, I will be online in the morning when this is going on. So if something comes up, if you have a question on the exam, send me an email, fire it at me. In fact, I'll probably have Zoom open just to remind people that roll into class. So if you pop into the Zoom room, you can just, you know, yell at me, and hopefully I'm paying attention. But I will answer any questions just as if I was in class. But other than that, I'm going to wish you luck. Do well. Don't let it stress you out. I know people freak out about this. Hey, it's just a test. I'm just looking to see what you know. And it's definitely not the end of the world, whatever the result is. Okay. So with that, have a great couple of days, or at least as good as they can be with the test looming. And I guess I will see everybody on Monday. All right. But I will be around as always. All right. So you guys have a great couple of days. See you later.